Hello, this is Miss Moore, and today during chemistry, we're going to discuss heat flow and temperature. Today's essential question: how does energy or heat flow through endothermic and exothermic processes? All right, we're going to start with a list of definitions or descriptions of temperature, heat, and kinetic energy and the relationship between them. So here we go. Thermochemistry is the study of energy and changes that occur during chemical reactions and phase changes. So thermochemistry is the study of changes of energy. We'll leave it at that for now. Okay? Kinetic energy. Kinetic energy is the energy of motion. Energy of motion. That's important. One more time. Kinetic energy is the energy of motion. All atoms, and we could actually make that more generic. We could say that all particles are in constant motion, which mean they all have kinetic energy. So all particles are in constant motion, meaning that they have kinetic energy. And the greater the velocity of movement, the greater the kinetic energy. And for us, for now, think of velocity as speed. That isn't quite right. But for now, that will work. So the greater the speed of the movement, that means there is more kinetic energy. So movement. Movement is really kinetic energy. And more movement, more energy. All right, heat. How did we just jump from energy to heat, right? Well, there is actually a relationship here. Heat, which we represent as a Q, is the sum of all the kinetic energy in a sample of matter. So, if heat is related to energy, and energy is related to movement, the more heat, the more kinetic energy. The more heat, the more kinetic energy, the more movement, and it goes the other way around too. The more movement, the more kinetic energy, that means more heat. Okay, so now we have a relationship between movement and energy and heat. And the unit we use for energy or heat is either joules or calories. So now, when you read on a package how many calories are in something that you're eating, that's based on how much energy or how much heat can be produced from that thing that you're eating. Anyway. So now on to temperature. Temperature is a measurement of the average kinetic energy or the heat of something. And in science, the unit that we normally use is either Celsius or Kelvin. And we'll spend a lot more time talking about Kelvin in future. And then we have this thing called absolute zero. Absolute zero is the theoretical lowest temperature possible at all, anywhere, ever. Okay? And absolute zero, which is 0 degrees Kelvin, is when there is absolutely no particle movement. There is so little heat, so little movement, so little energy, no movement, absolute zero. Okay, So because we're going to be dealing with temperature, heat, energy, we should practice how to convert between units. Most of us are familiar with degrees Fahrenheit, which we don't use much in the sciences. So here is a equation you can use to switch back and forth between degrees Fahrenheit. So degrees Fahrenheit and degrees Celsius. So degrees Fahrenheit equals the degrees Celsius times 1.8. That is all divided or added to 32. So let's try a couple quick problems. Let's say I had 72 degrees Fahrenheit, and I want to know what that is in degrees Celsius. All we got to do is plug this in, right, into our formula here. So we're going to have 72 for Fahrenheit equals degrees Celsius, we don't know what that is, times 1.8 plus 32. So now we're solving for x, or in this case, c. So the first thing to do would be to get rid of that 32. So if we subtract 32 from both sides, we end up with 40 degrees equals degrees Celsius times 1.8. And then to get the degrees Celsius by itself, we can divide both sides by 1.8. And that will give us a degrees Celsius. If I did this right in my calculator, I got 22.2222 and so forth degrees Celsius. Pretty easy. All right, let's try one where we know the Celsius and we're trying to find the Fahrenheit. So if I had, let's see, how about 24 degrees Celsius, which is about room temperature. What is that in Fahrenheit? This is an easier one even to do. So we're going to have Fahrenheit equals 24 degrees Celsius times 1.8 plus 32. So we can start by multiplying the 24 by 1.8. And I hope some of you are checking up on me and not just believing that I'm going to punch these all right in my calculator. I got 43.2 plus 32. So that gives us 75.2 degrees Fahrenheit. So 24 degrees Celsius is 75.2 degrees Fahrenheit. Okay, and the next equation is converting between Kelvin to degrees Celsius back and forth. Kelvin is not a temperature unit that is normally used in everyday life, but it's a temperature unit used often in science. So we'll try one quick practice problem with this. If I had something that was, what should we say, 100 degrees Celsius, what is that in Kelvin? Well, that's pretty easy, right? Kelvin equals 100 plus 273.15. So it would be, too bad I don't know how to do math. Here we go, try that again. 373.15 Kelvin. So the actual procedure for figuring out Fahrenheit to Celsius, Kelvin to Celsius, back and forth, pretty easy. All right, onward. All right, energy unit conversions. The common energy units, which were earlier in the lecture, can be J for joules. It could also be cal for calories. And often, instead of joules or calories, we use kJ, which would be kilojoules. Or we could have kcal, which is kilocalories. And truthfully, what is used most often instead of kcal, we represent that also as cal, but capital C. So capital CAL is really kcal, whereas lowercase cal is calories. All right, so now, what is relationship between joules and calories? And then we'll try to do a quick practice problem. So here is our relationship here. 1 cal, that's little cal, equals 4.184 joules. So let's say I had, should make it a little bit tricky, just a little bit, 272 cal, capital Cal. And we want to know what that is in joules. So the first thing we would need to do is turn this cal, which remember is really kcal, try that again, kcal, into lowercase cal, right? So this is one of those move the decimal things, right? So let me get rid of this. A little room to write. We're going to end up moving the decimal to go from capital Cal to lowercase cal. That's like basically going from kilo to base. So that's 3 moves. 1, 2, 3. So our new question is 27200 little cal to joules. All right? And now we can use this handy dandy equality right here, set up a t-chart, and we're good to go. So we're going to have 27200 cal over 1. And then we're going to use this guy here, putting 1 on the top, 1 on the bottom, setting them up so that the units cancel out. And since we have cal here, we need to have cal at the bottom. So we'll have 1 cal at the bottom, and then 4.184 joules at the top. Cal crosses out cal. So now we multiply across. And if I did my calculations correctly, I got 1,138,048 joules. And while the question didn't ask us to do this, we could turn this into kilojoules. So let's just do that for practice. So going from joules, which would be the base because there's no prefix, to kilojoules, we're going to be moving the decimal 1, 2, 3. So final answer would be 11380. Oops, forgot the decimal. 048 kJ. All right, so that's really all there is to energy unit conversions. And so let's move onward. All right, a few terms you need to know before we start talking about endothermic and exothermic. So first is a system. The system is the reaction or object being studied. Okay, it's what the question is about. It's what we're thinking about. Whereas the surround is the environment the system is in, the things in contact with the system. So for example, if my question was something like, at what temperature does ice melt. Okay, and so we're going to do this experiment. Yes, you get to see my drawing abilities, which leaves much to be desired. So here I have a beaker, that's a beaker, and in it I have little ice blocks, little pieces of ice. Right here, ice, ice everywhere. All right, and I should have some sort of thermometer sticking in there. There's my thermometer. So in this case, what is the system? What is the surround? Okay, well, the system is the reaction or object being studied. And what do we care about? We care about ice melting. So what do you think the system is in this case? The ice. The ice is the system. And what is the surround in this case? The surround is the environment the ice is in. So the surround could be the beaker and possibly even the air surrounding the beaker, right? System, surround. System, again, is the reaction or the thing, the object we're talking about, we're studying. And the surround is the environment the system is in. It's the thing in contact with the system. The reason this is a big deal is that you're going to find in some experiments that even though we care about the system, we can only measure the temperature or whatever of the surround. So you kind of have to think about what you're measuring versus what you're really looking for. And that'll make more sense in a little bit. All right. In thermochemistry, the direction of heat flow is given from the point of view of the system, the thing that we're studying. And that will also make sense in a moment. All right, on to exothermic processes. So, definition of an exothermic reaction is a process that releases heat. And I am horrible about memorizing things, so I used to have trouble remembering exothermic and endothermic, which we're going to talk about next. So a little trick that helped me is that exothermic, the heat is exiting. Exothermic, heat is exiting. Okay, it's exiting the process. So, what's happening during an exothermic process is that the system is losing heat to the surround. As the process continues over time, the system, the thing we're studying, will cool down because it's losing, and the heat, the surround is going to heat up, right? Because the heat is exiting the system into the surround. Now, think about this. Go back, think about the beginning of the lecture. If the system is cooling down, what's happening to the energy in the system? Is it increasing, decreasing, or staying the same? Well, the system is losing energy and the surround is gaining energy. Okay, on to the last topic, which is the endothermic process. So during an endothermic reaction, it's a process that is gaining or absorbing heat. So what's my trick for remembering this? Endothermic, heat is entering. Okay, so during an endothermic process, heat is entering. Okay, so in an endothermic process, the system is absorbing heat from the surround. So think about this. What should happen to the temperature of the system if it's absorbing heat? Temperature should increase or go up. And what should happen to the temperature of the surround? It's going to go down because it's losing heat to the system. So as the process continues, the system will heat up and the surround will cool down. And energy, what should happen to the energy? The system More energy, less energy. More energy because more heat, higher temperature. Surround, less energy. And that's written there. All right, so let's go back to our ice example really quickly. So here's my lovely drawing of ice in a beaker. So what kind of process do you think this is? Ice melting. Is that an endothermic process or an exothermic process? Well, think about what's happening. And by the way, cold, there's no such thing as cold. I mean, I know you feel cold. We talk about it. There's a word for it, but there's no physical thing for cold. There's only heat. So for ice to melt, what needs to happen? The ice needs to gain heat, right? So heat is going from the beaker and the air into the ice. So heat is entering into the thing we care about, the system, the ice. So if heat is entering, this would be an endothermic process. If we were freezing ice, on the other hand, if we were taking water and freezing it, we would need to remove heat, right? So heat would need to exit, and that would be an exothermic process. Okay, that's it for today. Have a good one, folks.